Hello and welcome to the logic of it all. This is our third video about graphs, and in this video we introduce the concept of a tree. In the previous video we talked about connected versus not connected graphs, and also we talked about the concept of a cycle in a graph. Now trees are defined using these two concepts. So a tree is an undirected graph where the graph is connected, which means that there is at least one path between every two vertices that you choose, and the graph doesn't have any cycles. So an acyclic graph, a graph without any cycles that is connected, is defined to be a tree. Now here are two examples. The question is, which one is a tree? If you look at the graph on the left, you'll see, you can easily see that the graph has a cycle. So from this node here, you can go here, then down, and then up, and you end up where you started, which means that the graph has a cycle, and trees are not supposed to have cycles, so this is not a tree. If you look at the graph on the right, it doesn't have any cycles, but it's not connected, because if we name these vertices A, B, C, and D, there is no path between, for example, B and D, or D and A, and so on. And as a result, the graph is not connected, and being connected is another condition of a tree. So for that reason, the graph on the right is not connected, is not a tree either. So neither one of them is a tree, but for different reasons. The graph on the left has a cycle, and because of that, it's not a tree. The graph on the right is not connected, and again, because of that, is not a tree. So a connected graph with no cycles is called a tree. Here are some examples of graphs that are trees. So the first example, if you have only one vertex, obviously it doesn't have a cycle and it's connected, and because of that it's a tree. With two vertices, if you connect them with an edge, then there is no cycle and it's connected, so it's a tree. With three vertices, this is an example of a tree. Again, it's connected and no cycles. Another type of tree with three vertices would be something like a line, A, B, and C, which is basically the same thing. But yeah, so these are examples of trees of different sizes. Now, this definition can be extended to the definition of a forest. A forest is a graph that has no cycles. Okay, an undirected graph with no cycles is called a forest. So it doesn't necessarily have to be connected anymore. And as you can see, this whole graph at the bottom with all these vertices A, B, C, E, F, G, H, I, J, K, the graph in its entirety doesn't have any cycles, and because of that, it's a forest. Now, another way to think about this is that a forest is a collection of trees, because if you look at each one of these components individually, it's a tree. It's a connected graph with no cycles. Each one of them is a connected graph with no cycles, so it's a tree. And the forest is a collection of trees. Now, for the applications that we are going to consider later, we usually like to identify one of the vertices in a tree as the root of the tree, and we usually put that on the top. So here, for example, A is the root of the tree. And as we will see in the next in the next slide, this is important, for example, when we want to define the concept of a child or a parent of a vertex, or descendants of a vertex, and ancestors of a vertex. So, and it's very intuitive. We will see the formal definition in the next slide, but we really don't need the formal definition. So for example, if you look at the vertex B, the vertices that are immediately below B are the children. So in this case, we have these two. So B has two children, D and E. And the vertex above is the parent. So for example, for B, if we go up, A is the parent. And similarly, the parent of D and E is B. Okay, so that's the concept of a child and a parent in a tree. And now the concept of a descendant is similar, which means that, for example, if you look at B, everything below B is called a descendant of B. So that includes D and E, and also F, G, and H. These are all descendants of B. And the concept of ancestor is the opposite of that. So for example, if we want to look at the vertex D, its ancestors are everything if we go above. So B and A are ancestors of D. Now here's the formal definition. So we have two vertices V1 and V2. If there is a path from the root that goes through V1 and then immediately from after V1 goes through V2, so there isn't anything between them, then we say V2 is a child of V1 and V1 is the parent of V2. Now, for descendant and ancestor, it's similar. So there is a path from the root going through V1 first and then V2, but it doesn't need to be immediate. So there may or may not be other vertices in that path between V1 and V2 in the context of defining an ancestor or a descendant. And finally, if we have a vertex that doesn't have any children or any descendants, then we call that a leaf. So for example, if this is our graph, A, B, C, and D. C and D don't have any children, so these two are the leaves of this tree. Another important concept that we will use later in trees is how far a vertex is from the root, and that is formalized by the definition of the level of a vertex. So the level of a vertex is the length of a path that starts from the root and ends at that vertex. For example, if you want to look at the vertex D here, so D is down here, we look at the path going from the root to D, so A to B and B to D, that's the only path. And the length of that path is 2, so we say the level of the vertex D is 2. So, and if you want to do that for G, for example, then we need to traverse one more edge to get to G, and that means that the level of G is 3. And similarly, the level of C is 1 because it takes only one edge to go from the root to C, and the level of the root itself is 0 because it takes traversing no edge to go from the root to A. So 0, 1, 2, 3 are the levels of A, C, D, and G respectively. Now again, in computer science, usually we focus on a special type of trees which we call binary trees. So the definition is very simple. In a binary tree, every vertex is allowed to have at most 2 children. So either no child, 1 or 2 children. Okay, and here's an example of a binary tree. As you can see, if you look at the vertex A, it has 2 children, namely B and C. If you look at B, it has 1 child. If you look at D, it has 2 children, F and H. And finally, F, H, and C, they don't have any children, which is allowed also, 0, 1, or 2 children. And if you remember from a previous slide, these are the leaves of the tree. So a binary tree is a tree where each node has at most 2 children. And usually it's easier for us to call these children left and right children of each vertex. So for example, if you look at A, its left child is B and right child is C, and so on. Now in this video, we are going to look at a couple of applications of binary trees, but later on we will revisit binary trees and see more applications. So the first one is, if we have a proposition such as P and not Q implies R, what we can do is we can represent this proposition instead of the linear representation that you see there. We can use a binary tree to represent this, and the benefit of doing that is that the inner structure of the proposition will be more explicit when we create a binary tree out of it. So the way to do that is the top level connective is AND. So we put AND on the top and then two children. On the left we have P. On the right we have this entire proposition, again, which is an implication. So we put implication here, and then it has left and right. On the right side of the implication, we have R. On the left side, we still have a compound proposition, which is not Q. So we put the connective not, and that has only one child, which is Q. So this is the binary tree representing the proposition P and not Q implies R. We can do a similar thing for algebraic expressions as well, with addition, subtraction, division, and so on. And usually this is what happens when in a programming language you have an expression like that and it's supposed to be evaluated. First, it is translated into a binary tree, which is called usually a parse tree, and then the evaluation happens. So here's our example. Let's see how we draw the parse tree for this. So again, we need to first recognize what's the top level operation here, which is this multiplication. So we put the multiplication on the top, and then it has a left and right. So on the left we have this entire thing, and on the right we have b plus c, which is simpler. So let's go to the right. So b plus c, the operation is plus. On the left it has b, and on the right it has c. And then on the left side of the multiplication, this multiplication, we have this entire thing. And again, on the top level, it's a division. So division is the operation, left and right. On the left side of the division, we have this, a times b. So it's the times where a is on the left and b is on the right. And then on the right side of the division, we have b minus c. So the operation is subtraction. B is on the left side and C is on the right side of the subtraction. So this is called the parse tree of that expression.